Okay, so I'm going to do this problem from Hibbeler having to do with 3D forces and force vectors. So you've got here a flower pot which has a mass of 50 kilograms. And this complicated system of cables are holding up the flower pot. And the question is, you want to find, for part A, find this distance d such that the tension in cables AC and AD is half as large as the tension in cable AB. So your strategy is always to kind of think about free body diagram and forces. So if I think about it, if I look at the point A here, I've got 4 forces acting, one from each of the cables, right? Like this. And then there's the tension in the cable downward, which is equal to the weight of the pot, right? Okay, so for those 4 forces, just to save myself some writing, I'm going to call these two have tension T, right? Magnitude of tension T. So I'm calling the magnitude of the tension AC equals the magnitude of the tension AD, and I'm just to save myself some writing, I'm just calling that T. Okay, that's the tension. And then there's also this tension in AB. So the problem says that the tension in cables AC and AD is half as large as the tension in cable AB, so I'll call this one here 2T. Okay, so I've got tension AC, tension AD, and tension AB is twice as big. Okay. And then we've got weight downward, I'll just call it W, which is mg, right? Okay. All right, so we've got those forces, and basically we have to apply the conditions of equilibrium. So our plan, anytime you have these kinds of dimensions here for cables, is the plan is going to be to write the tensions in Cartesian form, and then we will apply the conditions for equilibrium. So we're going to apply the sum of the forces in the x direction equals to 0, the sum of the forces in the y direction equals to 0, and the sum of the forces in the z direction equals to 0. So that's our plan. So it's pretty straightforward, maybe a little bit tedious, but not too bad. So I'll just go ahead and execute the plan, starting on the next slide. Okay, so we need to represent all of these forces in Cartesian components. Notice that point A is at the point 0, 0, 0. So I'm going to label all these components just with their x, y, and z coordinates for the cables. So for example, let's write out, what would I write for the tension AD? I'm going to write it, it has a magnitude, TAD, and then it has a direction, and that direction is denoted by this unit vector AD, a unit vector which points from A to D. Okay? So anytime I know these kind of coordinates of the cables, I can write the Cartesian component of TAD using this method. So let's write this out. We said that this, just to save myself writing, we're just calling this T, TAD, and then a unit vector which goes from A to D. So let me write it like this. XD I hat plus YD J hat plus ZD K hat divided by the magnitude of that vector, so xd squared plus yd squared plus zd squared. Okay, so this thing here is a unit vector which points from A to D. The numerator is a vector which goes from A to D, and then I divide by the length to get a unit vector. Okay. Now I need to do the same thing for AC and for AB. So the idea is exactly the same. I'm going to use a couple of sort of nice things just to simplify my life. Notice that XC is equal to XD, YC is minus YD, and ZC is ZD. So I'm just going to sort of simplify my life by using that. And you can also notice that YB is equal to 0. Okay? So for the when I'm doing cable AB, I don't need to worry about a Y component. Okay, so the strategy is the same. So let me pause the narration and write out those components for the other forces. Okay, so there are the others. Notice that my formula for TAC looks almost the same as for TAD. The only difference is there's a minus sign here because the Y component for AC is negative compared to the Y component for D. And then TAB looks similar, it's just that there's no Y component because the cable AB is acting on the x-axis, so there's no Y component. Okay, it's acting in the xz plane, so the Y component is 0. Okay, so those are our forces, and now we just have to apply the conditions for equilibrium. We need to apply the sum of the forces in the x direction is equal to 0, sum of the forces in the y direction equals to 0, and the sum of the forces in the z direction equals to 0. So I'll do that on the next slide. Okay, so let's add up the x direction. Sum of the forces in the x direction equals to 0. So I have to grab all of the I components. So I've got this one, and this one, and add them up and set that equal to 0. So what I'm going to get here for this equation is I'm going to get, you see the first two, this one and this one, are the same. So I get 2t xd divided by the square root of xd squared plus yd squared plus zd squared. And then I have this third one plus 2t xb over the square root of xb squared plus zb squared. Has to equal to 0. Okay. Now, notice something nice happens, that there's a 2t in both terms, so those cancel. And now think back to what I'm trying to find. I'm trying to find d, which is zb. So the thing I'm trying to find is right here, zb. And everything else in this equation, the x, the y, and the z, I know all of the coordinates of everything. So all I need to do now is solve for zb. Okay? Solve this equation for zb. So I just have to do some algebra in order to solve that equation. So I will do that on the next slide. Okay, so there's the equation. I'm just trying to solve this for d. So now it's just a math problem, a little bit tedious. So just to save myself some time, I'll pause the narration here and I'll just write out the algebra, solving for d there, and you can see the answers. Okay, so a little bit of algebra. I simplified my life by canceling out these two terms here because they're the same on both sides, xb xd squared. And then I solve for d. I have to be a little careful about plus and minus signs. Clearly d needs to be a positive number from the picture. Plugging in the numbers, I get d is the square root of 13 meters. Okay, and if you plug your numbers, if you want the numerical value of that, it's 3.61. Okay, so there's the answer to part A. We've gotten now D such that the tension in cable AB is twice as big as the tensions in cables AC and AD. All right, so then we'll move on to part B. Part B is just asking what is that tension, right? So now I have one other thing that I don't know, which is the tension in each cable. Okay, so moving on to part B now. What is the tension in each cable? So now our new target is T, right? If I know T, that tells me the tension in AD and AC, and then I just have to double it to get the tension in AB. So we have to use either sum of the forces in the y direction equals to 0, or the sum of the forces in the z direction equals to 0. The x direction we already used, so we can't use that again. And if you look at this, the y direction doesn't tell me too much, because if all I have is that this one plus this one has to equal 0, but we already know that, right? We know from the symmetry of the situation that the y component of TAC is equal to minus the y component of TAD, right? So the y direction doesn't help too much, but the z direction will help, right? So let's count all of our z components. This one, this one, this one, and this one. Don't forget about the weight there. Add all those up and set it equal to 0. So we're doing here the sum of the forces in the z direction equals to 0. What equation do we get out of that? Well, again, the first two are the same. So we get here 2t zd over the square root of xd squared plus yd squared plus zd squared. The second one is 2t d over the square root of xb squared plus d squared. And then we've got to, don't forget about this weight downwards, mg minus mg equals to 0. So there's the equation that comes from the z direction. And this equation, the target is t. And everything else I know. I know xd, I know yd, I know zd, and I know the mass of the pot, right? So all I have to do now is just to solve this for t, okay? And then we've solved the problem. So I'll finish that on the next slide. Okay, so there's the equation which I wrote from the previous slide. We just need to solve this for t. So I'll just do a little bit here, and then I'll sort of skip over the details. Let me pull out a t and divide by a 2. So I'm going to have t zd square root of xd squared plus yd squared plus zd squared plus d over xb squared plus d squared equals mg over 2. Okay? And basically, I have everything done now. I just need to plug in numbers into here and into here and solve for that t. So let me plug in the numbers, and I'll pause the narration, and then I'll let you see the answer. Okay, so I just plugged in the numbers and did a little bit of algebra. So just remember that from the previous part we had solved that d was the square root of 13 meters. So d squared down here is 13 meters squared. And plug in the numbers, you get a formula which is not too complicated, 7mg over 2 squared 3 plus the root 13. And the numbers there work out to be 259.6 newtons for t, right? So remember, t was the magnitude of TAC and was equal to the magnitude of TAD, which is about 260 newtons, okay? And then TAB, remember the problem set was twice as large, right? So that's 2t. So if you multiply that by 2, you get about 520 newtons. So there's your answer to part B. putting in the numbers there. So I hope you found this useful. It's a very simple, I mean, the algebra is a little complicated, but strategy is always the same for these kinds of problems. Represent all of the forces in Cartesian components, and then add up the forces in the x, y, and z directions and make sure that they equal to 0. You're going to get a set of equations which you need to solve. And so at that point it becomes a math problem. The hard part is setting it up, representing those forces in Cartesian components.